Welcome back everyone. I hope you all had the chance to recharge your batteries and digest what we've learned so far. Let's dive back in and continue learning together. Alright, let's move on to creating the second scene. Before we begin, let's take another look at the finished reference video, which can be found in the storyboard folder under scene 002. We're dealing with a relatively simple animation in this scene. Our structure will be rotating 180 degrees around the x-axis. The light source will be in a fixed position for this scene. Additionally, we'll animate the color of material ID 3 and 4, the MPL and the flow channel at the beginning and end of the video, and set it to black to create a seamless transition from the first scene and to the third scene. So let's get started. We bring the video editor back to the foreground and save a new file called scene-002-A. And we also change the name in the output options directly to the new scene name, so that we don't overwrite our videos later when we render. And save again for good measure. Let's make all the properties visible again. There's a button down here called Show All that we can use and delete all the old keyframes out with a right click and remove group. Next, in Geodict, we will head to the Camera tab and reset the view with the Reset View button. This will reset all the values we find under Camera 3D in the visualization settings to the default ones. If you are still in light source navigation mode, you can switch back to the camera control here at the top, in the toolbar on the icon to the left of it. We'll now proceed to block the first position of our animation. This time, we'll be using the numeric input in the Camera tab. To improve visibility in the visualization area, I will close the sidebar when not needed. We will utilize the field's rotation X, Y and Z for a direct rotation around the corresponding axis. We first rotate the Y-axis about plus 90 degrees to look at the long side. Next, we rotate around the X-axis about minus 90 degrees to look at the MPL. With the right click or the mouse wheel, we now zoom in so far that the structure fills the entire view. This should fit well with the translation Z of +7. In the video editor, we will press Pull Keyframe. In the Track Properties dialog, we will deselect all fields except the property Camera 3D Local Rotation. This is the property we set here in the Camera tab. We also make sure that we move the newly created keyframe to frame 0. We also want the scene to be about 4 seconds long, so we set a playhead to frame 120. Next, we switch back to Geodict. We want the structure to rotate about the x-axis 180 degrees to the side of the flow channel. We want it to rotate from the top to the bottom. To be sure in which direction the values should change, we test briefly how the direction of rotation is when we change the values. Yes, that looks correct. So we can enter for X plus 90 in the rotation field. In the video editor, we now click on Pull Keyframe again. Then we click play to evaluate the animation. Yes, this looks quite good. We'll make a few more adjustments to the curves to make the movement look more dynamical. We will hide all properties for now except for the local rotation. Alright, let's add some dynamic movement to our animation by switching the interpolation for the x-axis to smooth. Go ahead and select all control points and change the interpolation from linear to smooth. You will notice that the curves have changed and the values before and after the control points now smoothly merge into each other. Also notice the two slopes fields that have been added below the interpolation field. Now, using the slopes value, we are going to adjust the rotation so that it slows down a bit towards the center. This will give our audience a better view of the structure in the middle. Also, we are going to hide the Y and Z axis since they are not animated. You can expand properties that have a small black arrow on the side and select and hide individual aspects of the property. In our case, we are going to hide the Y and Z axis. We can read the movement around the x-axis from the curves as follows. We have the rotation starting slowly, picking up speed in the middle, slowing down again and ending smoothly. But we want the animation to slow down in the middle to get a better look at the structure. And we want it to play linearly at the beginning and the end, as if it was spinning all the time with a constant velocity. To achieve this, we will use the slopes feature. Now we will select the first control point and adjust the first slope value to 2. The first slope value affects the values coming from the selected control point. Then we will move on to the second slope value, which influences the interpolation that ends at the next point. We will change the value also to 2. We play it to test how it looks now. The structure turns briskly into the picture, slows down towards the center without stopping, and then turns briskly out of the picture again. So we can already be very pleased with ourselves. We stop the animation and then save the result. Next, we are going to animate the last part of the scene, the changing of the color for Material ID 3 and 4. To animate the color of Material ID 3 and 4, we will navigate to the last frame in the video editor and place the playhead on frame 140. Then we open the Color and Visibility dialog in the Geodict sidebar. We will change the color for Material ID 3 and 4 to an absolute black using the Select Color dialog. This one here. And again for Material ID 4. Then go back to the video editor and press Pull Keyframe. The Track Properties dialog should appear again. There we select only Color Material 3 and Color Material 4 and click OK. We work our way through again similar to the first scene by hiding everything except Color Material 3, then selecting the first control points, placing them on frame 10. Next, we select the last control points, placing them on frame 0. A quick note on how control points work in the video editor. Here we see the curve form of how the color of Material ID 3 changes from black to red. After frame 10, there are no more control points and the value of the property is automatically held. The same applies in the reverse, as we will see when we set the first control points for Material ID 4. Geodict will hold this value until it changes. We now use the same procedure for Color Material 4. We hide Color Material 3 and display Color Material 4. Let's go and find our control points first. Here they are. We have already obtained the value by pull keyframe. Now we will move the control points on frame 120 to frame 110. Next we move the control points on frame 140 to frame 120. Once we've completed that step, we can then proceed to delete the keyframe again at frame 140. As always, it's important to save your work regularly. And after all these steps are done, we will have a look at the result. And then we play the video and see if everything is now to our satisfaction. That all fits so far. We have now completed the second scene and move on to the third one. We stop the playback first and then open up the storyboard folder. Again, we will first look at the reference material in the storyboard folder in folder Scene 003. Alright. We're gonna start by flying backwards through the float channel, keeping in mind we come from a black background. That's gonna be our first 2 time points to block. Then we're gonna turn the structure around and stop on its side. That's the next and third time point we wanna block. Finally, we're gonna align the timings and make sure the movements are nice and smooth before we proceed. Let's start fresh and create a new scene. We will call it Scene -003 -A. We will first change the name in the output options to Scene -003 -A and then save the file also with the name Scene -003 -A. We will now delete all the keyframes again. Quick tip, press Show All down here and then Center View to bring all the keyframes into view. We can also delete the property Color Material 3 and Color Material 4 because we don't want to animate it in this scene. By right-clicking on the list item, we can select Remove from the menu to delete it. We also need to check that the color changes of Material ID 3 and 4 are not still present. The easiest way to do this is to simply load our saved visualization settings from the beginning. We go to the sidebar, under Visualization and select the load icon down here. Then we navigate to the code folder and double-click visualizationsettings.py to reload our colors. We switch to Geodict and go to the Camera tab and click on Reset View again. This is the quickest place to begin. We will start with the first keyframe we want to block. We are not starting at time 0 though, because we have no visual reference at frame 0 to set the camera correctly. That's why we are starting at the second point in time after the fly-through of the float channel, right before the turn. In the storyboard folder of the scene, we can open the corresponding image to orient ourselves. Alright, let's align our camera to the reference image. It's a quick and easy process. All we have to do is zoom in. But as we compare our view with the image, we can see that it's not quite right. The float channel appears longer and narrower at the end, and we are not seeing as much of the top of the fibers as we should. No problem, we can easily fix this by adjusting the camera's field of view. The field of view of a camera is the extent of the observable world that is captured by the camera's lens. A higher field of view in decrease captures a wider angle of the scene. To adjust the field of view, we open the visualization settings in the sidebar by clicking on the gear icon. Once inside, we look for the field of view element. By default, it is set to 20. We increase it while every now and then positioning the camera closer to the structure again, until we hit the look of the reference image. A value of 50 for the field of view fits well. We keep 50. We also see directly that the camera is still too low. We rotate the camera down a bit via rotation X. A value of 2 degrees fits very well here. We switch to the video editor and click Pull Keyframe. The Track Properties dialog should appear and offer us the property Field of View. Every other property we deselect. Then we click OK. We move the keyframe roughly to frame 120. We will take care of the right timing in a moment. First, capturing these key positions counts. For the next step, we make sure that the playhead is to the left of the first keyframe and switch back to Geodict. Now, let's talk about one of the challenges when planning camera movements in Geodict. Typically, when we are looking to zoom into a structure, like the end of the flow channel, we would simply move the camera forward to the end of the flow channel. However, in this case, we end up slightly inside the fibers. The reason for this is that even though we are talking about positioning the camera, we're actually moving the camera but rotating the structure. That's why when we move the camera forward, we end up inside the structure. But don't worry, this isn't an unsolvable problem. It's just something to keep in mind when creating videos with Geodict. For the time being, we move to just before the end of the flow channel. This way we can better adjust the camera so that it also flies surely over the fibers. Then we adjust the translation Y value so that we are no longer inside the fibers, but slightly above them. In the storyboard folder, there's also a reference image that we can consult. Using the reference image, we now match our camera. Personally, I will use the direct numerical input here so that I only influence the translation Y value and nothing else. With the value of -0.07, we hit the picture quite well. Now we zoom in a bit further until there's no more structure to be seen, and we are done. Back to the video editor and click Pull Keyframe. Ignore any upcoming track properties that might appear. We place the new keyframe on frame 0. Then test the animation. Very good, we don't fly through the geometry unintentionally. To match the timing, let's look again at the reference video in the storyboard folder. We stop the video at the point when the rotation starts. We should be about 3 seconds in the timeline, so we'll take 3 seconds as an initial guide. Back in the video editor, we position our second keyframe at frame 90, 3 seconds. And we save our progress. Now let's move on to the last point in time we want to capture when we are looking at the long side of our structure. To do this, we'll place the playhead again beyond the last frame, open the last reference image, in the storyboard folder as a reference and then switch back to Geodict. First, let's rotate the structure properly into the frame. Personally, I prefer to use the direct input in rotation X, Y and Z for this, as it offers more control and precision. And it's easier to understand because we're directly influencing the axis. First, we will set X back to 0. Then we'll take a look at the rotation around Y in steps of 10 degrees to see which direction we need to rotate in. We'll rotate in the positive direction and enter 90 degrees in Y. Now we will zoom out a bit more until we reach the same position as in the video. Great, the field of view also matches. The last step is to adjust the light source so that the lighting matches the reference image. Let's switch to the light source navigation and adjust the light until it matches the reference image. Now everything fits and we can switch to the video editor to create a keyframe via Pull Keyframe. We'll open the reference video again and take a look at how long we should animate the rotation. We will start at second 3 and let the video play until the structure stops. That should be at second 7, so 4 seconds or 120 frames that this movement should last if we go by the reference. We go back to the video editor and position our third keyframe at frame 210. Finally, let's let it play to see if everything looks good. Very good. At the end, it's a good idea to let the structure remain for a few seconds so that the viewer can take in the entire structure again. Let's try 2 seconds, that is 60 frames, and that would be frame 270, where we have to set the playhead. Now we can just click Pull Keyframe because we just want to hold the last position. We center the view and play again. Very well. We have now done the rough blocking for the keyframes and the timing. Now let's make sure that we get the rotation nice and smooth and let it swing out briefly at the end. We stop the video editor and hide all properties except the local rotation and center the view. We can also hide the Z-axis for now as nothing is happening there. Next, we will select the control points that make up the rotation here and here, and then we will set the interpolation to smooth to make the animation smoother. To see the effect, we play the animation. The movement is better, but it still doesn't look quite good. To work more efficiently, we can zoom in on the rotation area. To get a better fit, we can also match the axis of the video editor independently by moving the mouse over the axis here and then using the navigation zoom or move. This will give us more control and precision when adjusting the animation. Since we're only interested in this movement now, let's take a look at another useful feature of the video editor, the set limits. Normally the video editor plays everything from the first to the last keyframe. With set limits, you can define a range that will be played. And when rendering the video, these limits will be taken into account. This allows us to focus on perfecting specific parts of the animation without having to preview the entire animation. We activate set limits and see two new number fields appear. Here we can define start and end. We select the range that is 10 frames before and 10 frames after our range of interest, in this case 80 and 220. Two markers will appear in the frame time bar up here, a green arrow marking the start point and a red arrow marking the end point. We can also move these arrows with the left mouse button directly in the bar. If we now press play, we can focus on exactly this area and make any necessary adjustments. One reason why the movement looks so unnatural and choppy is that the tracking shot ends and then the rotation happens. But the movement should flow smoothly into each other. A simple solution to this is to overlap the control points. We display the z-axis of the property, translation, and select it. Then we click on Center View. And we select the first control point of translation Z on frame 0 and set the interpolation value to smooth. We set the first slope value to 1 so that the motion remains linear. We leave the second one at 0. Next, we select the second control point of translation Z and position it on frame 120. Now we move on to the y-axis of local rotation. We orient ourselves so that we have a good view of the second control point and then select it. We now move the control point 10 frames to the left, in this case to frame 80. We adjust the set limits so that it starts playing 10 frames earlier at 70 and look at the animation. Much better. The rotation no longer starts abruptly and the entire movement merges smoothly. Okay, so at the end of our camera pan, we're going to add some oversteer, correction and bobbing. This will give our scene more weight and dynamics, making it look like we're moving heavy equipment that needs time to slow down. To do this, we are going to go to the control points at the end of the camera pan and match our view accordingly. The key is not to overdo it. We want to create small movements that don't take long at all. That's why I'm zooming in real close here and using the numerical positioning of the playhead to go through the animation slowly, step by step. That way we can get a feel for the timing we need to apply here. I'm clicking through the frame slowly but at a steady pace. Okay, so we want to keep the oversteering and rocking to a minimum, around 20 frames. So 20 frames later, at frame 230, we're going to create a new control point. We first select the local rotation Y curve in the properties window. Then right-click on the curve at frame 230 and select Interpolate Selected Properties. This way we get a new control point drawn directly into the curve, but all other properties remain untouched. We want to make sure that the new control point sits on the right frame of 230, so we adjust it. We will now move the old control point on frame 210 up 2 to 3 degrees so that the rotation goes to 92 or 93 degrees. We can do this quickly by hand, or we can use the numerical input. For the playback, we adjust the set limits to 190 and to 250. Now we play it. When we play it back, we see that it still looks pretty choppy. We need to hold the position longer when we overdrive. We will match our view so that we see the control points of frame 210 and 230 in their entirety here. Then we select only the y-axis of the local rotation property. Some frames to the right of frame 210, we right-click on the curve and select Interpolate Selected Properties. From the menu again, make sure that you do not click too close to another point. Otherwise, the new point automatically snaps to the existing keyframe and overlaps the old control point. The problem can then be solved by selecting the point and then moving it to a new frame via hand or via frame time. We make sure that the distance between the control points is 2 frames, and we also make sure that the interpolation is set to smooth again. The value of the new control point should be the same as the old control point. We either do this by eye and mouse or use the numerical input here. As a final icing on the cake, we adjust the second slope of control point 212, the one that affects the curve towards the next control point. We change the value to -2. This pushes the curve past the end of the value before it ends at the control point. This gives another little bounce at the end and makes our animation look more dynamic. We briefly check the set limit settings that we see the entire animation from frame 70 to frame 250. Then we play the animation. Finally, we let the camera tilt a bit as soon as the rotation starts to give a feeling of inertia and centrifugal forces. Before we do that, we will stop the playback and save. First, we hide all properties, and then we display only local rotation in Z direction. We adjust the view so that we can easily see the range of the rotation here, frame 90 to 210. We already have control points at frame 90 and 210. We need one more at 80 so that the camera does not tilt until the rotation begins. At frame 210, the camera should already have aligned itself properly. We zoom a bit into frame 80 and make sure we have the local rotation Z-axis selected. Then we right-click on the curve at frame 80 and select Interpolate Selected Properties. We select a control point at frame 90 and change the value by mouse or numeric input to 20. In order for the visualization area to update, we move the playhead so we can see our changes and touch them up. To better match the timing of the tilt around the Z-axis to the rotation of the Y-axis, we activate the Y-axis in the properties. Move the control point on frame 90 of the Z-axis so that it's approximately centered in the Y rotation. Still here and there a little touch up, for instance, changing the interpolation to smooth. Then we will take another look at the animation. We move the control point on frame 210 on the Z-axis another 10 frames to the left to frame 200. And then play it again. So far, so good. If you want to do a little diligence later, you're welcome to add an override of the movement on the Z-axis. For now, we take this and save. Great. So we've successfully blocked and finalized 3 scenes using our storyboard as a guide. This approach allowed us to effectively plan out camera positions, timings, and any necessary animations. It's a solid workflow that can be applied to bring any video concept to life. Now that we have our video files, we need to figure out the technicalities of bringing it all together to create the final video. The easiest way is to use the video editor. We have already set all the output options when we created the scenes. But before we hit run, we need to disable set limits. Otherwise, Geodik would only render out this section of our animation. We deselect it and save again. Now we can click on Run here below, and Geodik starts rendering our video. In the visualization area, we see a live update and can monitor the process to see if something unintentional happens. This will take some time, and for the purpose of this workshop I will skip ahead if I need to. We will need to do this manually with all our scenes and then edit the individual scenes into a single video using a video editing software. At this point, the free version of DaVinci Resolve should be briefly mentioned. So why did we create individual scenes in the first place and didn't compose everything in one scene in the video editor? This may sound tempting at first, until you get to the point where you lose track of how many scenes you have and how many properties you want to animate. In addition, you may want to show other structures in the same video or animate simulations with time steps, for example, filter lifetime simulations. However, we can solve the problem of manual rendering thanks to Python. In the workshop data there is a runme.py. Due to the need to be able to create videos more efficiently and clearly, we have developed a small Python framework for video rendering. This framework looks for the GPS save files of the video editor, renders them one after the other, and finally cuts them together as a single video. The important thing here is that the order of the scenes in which they need to be rendered is specified by the name. The script looks for the files in the code folder. Before I go into detail about how this framework works exactly, let's run it first so we can look at the result together right away after it has finished. Before we begin, we need to make sure that we are not in the navigation mode of the light source. Otherwise, the position helper of the light source will be rendered as well. To do this, we need to switch to the mouse navigation mode. You can do this by clicking on this icon here. Now, via the macro menu, we open the execute macro/script dialog. In the folder WS Visualization, we select the file runme.py and click on Run. A dialog will appear, where we can choose a video name, a base settings file that will be loaded at the beginning of each scene, and we can choose which of our scenes we want to render. Here we select all of them. We can still match the video name. I will leave it at the default for now. If you see an empty field for choose a base settings file, you can click on Browse and choose the setup file we created at the beginning of the workshop. With a click on OK, Geodik starts rendering. So long we can have a quick look at the framework. Let's open the project folder. Two key files to focus on in our framework are runme.py and main.py in the code folder. Runme.py should be placed directly in the main project folder, while main.py should be placed within a subfolder called code, located in the main project folder. It's also important to keep any video data GPS files and additional Python files within the code folder. If anyone has any questions or would like to learn more about how the framework functions, feel free to take a closer look at the Python files and make any necessary modifications. Once again, I highly recommend the GeoPy workshops conducted by Janine Hilden and Dominic Michel to anyone interested in learning more about working with Python and Geodict. They are experts in their field and will provide valuable insights and hands-on experience. It's important to keep in mind that different scenes may require different configuration files, rather than using the one selected through choose-a-base settings file. To handle this, you can simply place a .py file with the same name as the GPS file in the code folder. This way the framework will execute this specific file for that scene, rather than the base configuration. This is particularly useful when loading different structures from scene to scene. For the sake of this workshop, I will speed up the time. And now that Geodict has completed the rendering process, we can go ahead and open the project folder and navigate to the output folder. You will see the individual scenes, the corresponding image sequences, and the final overall video that we can now review. We accomplished a great deal in our 90-minute workshop. While there may be room for further optimization, it's normal to have areas for improvement. The beauty of this framework is that we can easily go back and make adjustments to individual scenes, and the video framework will handle the rest. This may require re-rendering, but the end result is a polished final video. In the project data of this workshop, you will find a Final Files folder which contains the final results of this workshop. In the scene 3, there is a small deviation at the end of the scene from what we've covered in this workshop. Feel free to use this as an opportunity to practice and apply what you've learned here. And there you have it, the conclusion of our advanced video production workshop. We explored the technique of scene blocking and learned how it can be used to efficiently create scenes for videos in Geodict, as well as how to enhance them to produce captivating videos of our structures and results that will effectively persuade others. We also gained hands-on experience with the Python video framework to assemble a polished final video from our scenes. I trust that the knowledge and tools provided during this workshop will help you showcase your products in an exceptional way in the future. Don't hesitate to reach out to us if you have any further questions or need additional support. Thank you so far for attending, and we look forward to seeing you again soon. We can't wait to see what you will create. Thank you again and have a great day.